Welcome back, focused learners, to another explainer. Today, we're taking on an absolute masterpiece of biological engineering, the human circulatory system. But we aren't just rattling off facts today. Oh no, we're building a complete, highly structured mind map. We've specifically designed this strategy to give you printable, complete content notes, all set against a high-contrast black background. Why? Well, because this design strips away all that visual clutter, making the information incredibly easy to memorize and literally perfect to reference whenever you need it. So go ahead and clear your distractions and let's map out exactly how your body stays alive.
Okay, let's dive into this. To truly master this system, we're going to break the body down into 5 specific architecture modules, which is going to perfectly prime your brain to categorize every single fact. We've got 1. Blood and lymph fluids. 2. Blood groups and clotting. 3. The human heart pump. 4. Cardiac cycle and ECG. And 5. Cardiovascular disorders and diseases.
Starting things off with Section 1. Blood and lymph fluids, the liquid transport network.
Imagine putting a vial of blood into a centrifuge and spinning it. It actually dramatically separates into 2 completely distinct layers. 55% of your blood is plasma, and the remaining 45% makes up what we call the formed elements. That's your red blood cells, white blood cells, and platelets. Now notice that plasma is overwhelmingly water. We're talking 90 to 92%. But the real magic? It's in the proteins suspended inside it. You've got albumin, which handles your blood's osmotic pressure. You've got globulin, kicking in to boost your immunity, and fibrinogen, which is absolutely crucial for blood clotting. In fact, fun little side note, if you take this plasma and entirely remove clotting factors like fibrinogen, you're left with what's known as serum.
Now, what's really interesting about this is this single, critical number, 120. This massive number represents the exact lifespan in days of an average red blood cell, or erythrocyte. And these cells are fascinating. They're packed with the iron-containing protein hemoglobin so they can transport gases. And they're actually biconcave in shape, with no nucleus. They're formed right in your red bone marrow, work tirelessly for exactly 120 days, and then, well, they're sent off to be destroyed. Their final resting place? The spleen. Yeah, the spleen is literally known as the graveyard of the red blood cells.
So while red blood cells are definitely the most abundant, white blood cells, or leukocytes, are the least abundant. But make no mistake, they are your crucial immune defenders. Here's exactly how their roles break down. You have neutrophils and monocytes, which perform phagocytosis. That means they literally eat foreign invaders. It's wild. Then you've got lymphocytes managing your broader immunity. Eosinophils kick into gear during allergic reactions, and basophils release really essential chemicals like histamine, heparin, and serotonin. And if you want a quick memory trick for their order of abundance, from most to least common, neutrophils are the most abundant, followed by lymphocytes, then monocytes, eosinophils, and finally basophils.
Of course, blood isn't the only fluid flowing through these physiological pipes. We've also got lymph. Lymph is this colorless fluid completely packed with specialized lymphocytes, meaning its primary gig is immunity. But it has another incredibly cool function. Deep inside your intestinal villi, there are these structures called lacteals, and lymph actively absorbs fats right through them. So it's essentially acting as an essential secondary carrier, transporting not just immune cells, but vital nutrients, hormones, and absorbed fats all throughout the body.
Let's transition over to our next branch, Section 2, Blood Groups and Clotting, Categorization and Cascade.
If you print out any part of this mind map for your notes, make it this matrix right here. It perfectly maps out how your blood group is entirely dictated by surface antigens. Basically, these are chemicals on your red blood cells that induce an immune response. Let's look at Group A. It has antigen A on the surface, but it carries anti-B antibodies floating in the plasma. That means Group A can safely receive donor blood only from Group A and Group O. Group AB? It's incredible. It has both A and B antigens, but 0 or nil antibodies. Because it has absolutely no antibodies to attack incoming blood, a person with AB can safely receive donations from AB, A, B, and O. On the flip side, Group O has nil antigens, but carries both anti-A and anti-B antibodies, meaning it can only accept blood from another Group O donor.
Let's move along and see how this all builds when the system actually takes damage and starts leaking. The second you get an injury, a really precise chain reaction called a cascade begins. First up, the injury activates your platelets, also known as thrombocytes. These activated platelets trigger the release of an enzyme called thrombokinase. Now pay close attention to step 2. This step critically requires calcium ions and vitamin K to actually proceed. Without them, it stalls.
Thrombokinase then acts on an inactive plasma protein called prothrombin, converting it straight into active thrombin. And finally, this thrombin converts soluble fibrinogen into a network of solid fibrin threads. This fibrin mesh acts like a net, trapping dead and damaged cellular elements to create your blood clot.
Heading further down the mind map, we hit Section 3, the human heart pump, anatomy of the engine.
Before we zoom into the human engine specifically, use this stark side-by-side comparison on the dark background to help your brain instantly categorize the two main circulatory pathways nature uses. First, we have open circulatory pathways. In creatures like arthropods and mollusks, there's literally no network of blood vessels. The fluid just washes directly over their tissues. But then we have closed circulatory pathways, which you find in annelids and chordates, like us humans. In a closed system, blood is strictly confined to this massive, complex network of vessels, your arteries, veins, and capillaries. And this closed loop, it's exactly what allows for much higher pressure and super precise regulation.
So, let's look at the anatomy of our closed system pump. The human heart actually derives from the mesoderm layer during development, and it sits perfectly protected in the thoracic cavity by a tough, double-walled membrane called the pericardium. It's got 4 distinct chambers, 2 upper atria, and 2 larger, highly muscular lower ventricles. Guarding the door between the right atrium and right ventricle is the tricuspid valve. Over between the left atrium and left ventricle, you've got the bicuspid or mitral valve. But honestly, the most vital piece of anatomy here is the sinoatrial or SA node. It's tucked right in the upper corner of the right atrium. This little patch of nodal musculature is autoexcitable. That means it generates its own electrical impulses to cause the heartbeat, literally making the SA node the natural pacemaker of your heart.
And this brilliantly illustrates where the iconic sound of a heartbeat actually comes from. You know that classic lub-dub you hear through a stethoscope? It's entirely mechanical. The lub sound isn't the heart muscles squeezing, it's the physical snapping shut of the tricuspid and bicuspid valves. The second sound, that dub, is caused by the sudden closure of the semilunar valves, which are the ones guarding the exits from the ventricles into the pulmonary artery and the aorta.
Let's shift our focus a bit. Section 4, Cardiac Cycle and ECG, the rhythms and electricity.
I want you to anchor this absolutely unforgettable decimal into your memory right now. 0.8. Think about it. If a normal human heart beats 72 times in 60 seconds, simple math tells us that a single beat takes exactly 0.8 seconds. This tiny 0.8 second window is the exact duration of one complete normal cardiac cycle.
Let's break down exactly what's happening linearly during those 0.8 seconds. It kicks off with 0.1 seconds of atrial systole. That's when the top chambers, the atria, contract. Immediately following that, for 0.3 seconds, you have ventricular systole. This is the massive, powerful contraction of those bottom chambers. And finally, for the remaining 0.4 seconds, the entire heart relaxes and fills back up with blood in a phase called joint diastole. 0.1 plus 0.3 plus 0.4. It is a perfectly timed, relentless sequential rhythm.
So, just how much blood is actually moving during these rapid-fire cycles? Well, during every single ventricular systole, the heart pumps out about 70 milliliters of blood. We call this the stroke volume. Now, to find your total cardiac output, you just take that 70 milliliter stroke volume and multiply it by your heart rate. Let's use the average of 72 beats per minute. 70 times 72 equals approximately 5,000 milliliters. To put that into perspective, your heart is pumping a massive 5 liters of blood every single minute of your life.
And we can actually map the electricity of this cycle using an electrocardiogram, or ECG. Those famous spikes you always see on hospital monitors aren't random. They represent the exact moments of electrical activity in the heart chambers. That first little bump, the P wave, is the electrical depolarization or excitation of the atria. Then you have that massive sharp spike in the middle, the QRS complex. That represents the powerful depolarization of the ventricles right before they aggressively contract. And finally, the T wave represents the repolarization of the ventricles, which is basically the ventricles returning to their normal resting electrical state.
Before we move to disorders, there is one highly specialized vascular highway worth a quick mention. It's called the hepatic portal system. Rather than blood just flowing straight from your gut back to the heart, this is a totally unique connection directly between the digestive tract and the liver. It ensures that all that nutrient-rich blood from your digestion gets processed by the liver first before it's allowed to join the general circulation.
Which brings us to the final node of our mind map, Section 5, Cardiovascular Disorders and Diseases, Glitches in the System.
So, the crucial point here is really clarifying the exact medical distinctions between terms we hear all the time but often use interchangeably. Normal blood pressure is 120 over 80 millimeters of mercury. When it chronically goes above that, you've got hypertension. Then there's coronary artery disease, also known as atherosclerosis, which is where calcium, fat, and cholesterol actually build up as plaque and block the specific vessels supplying the heart muscle itself. If that blood flow gets too low, the lack of oxygen triggers acute chest pain, which is called angina pectoris. Now here's where being precise really matters. A heart attack occurs when the heart muscle tissue actually begins to die due to a lack of blood supply. Heart failure, on the other hand, is when the heart hasn't stopped, but it's failing to pump blood effectively enough to meet the body's demands. And finally, cardiac arrest is when the heart suddenly and completely stops beating. 3 distinct terms, 3 very different medical emergencies.
To wrap things up, I want to leave you with a provocative thought that really brings this whole map together. We learned earlier that the human heart is myogenic, meaning its normal activities are auto-regulated by its own specialized muscles, like the SA node, entirely without the brain. However, there is a special neural center in the medulla oblongata of the brain, along with adrenal medullary hormones that can step in to increase or decrease your cardiac output. So, if the heart generates its very own beat, but the brain has the power to modulate it, what would actually happen to your pulse if that neural center in the medulla oblongata just completely stopped sending signals to your chest? It's an incredible testament to the sheer resilience of our circulatory system and definitely a mystery to ponder until next time. Keep this highly visual, printable mental map handy for your notes, use it to study, and as always, stay curious, focused learners.